The equations that we've been using, such as the ideal gas equation and the gas law, they are dependent upon some assumptions, the ideal gas assumptions. In fact, it's the ideal gas law equation because we're assuming that the gases are behaving ideally. That is, number one, your particles that are moving are points of negligible volume. Compared to the size of the container, the particles, which are so spread out, have almost no volume. There are neither attractive nor repulsive forces between the particles. The particles are so far apart, and they're moving so quickly that they have no effect on each other. And finally, particles, they move randomly and collide with elastic collisions. That is, there's no gain or loss of kinetic energy between those two particles. And so what effect will changing the pressure and changing the temperature have on these assumptions and therefore our equations? Well, what if you increase the pressure of a gas? You can do this, for example, of the gas in this container. By increasing the pressure, by pushing harder down, you'll be decreasing the volume of that container. And by decreasing the volume of the container, you'll be pushing those particles closer together. So they'll have greater attractive forces between them. They'll be near each other more often. And also, they'll make up a greater proportion of the volume of the container, so the relative volume of those particles will increase. And so, by increasing the pressure of a gas, you make it follow those ideal assumptions not as well. And therefore, by increasing the pressure of the gas, you'll make it less ideal. And changing the temperature. If you decrease the temperature of your particles, you'll be decreasing the speed of those particles. And because then they're not zooming by each other, but they're going slower, they'll have more time to interact with each other. But also, being in a lower temperature state, they'll exist in lower energy states as well, which usually are associated with higher particle attractions. At low temperatures, particle attractions become more important, and so particles will be held closer together, and they'll interact with each other more at those low temperatures. And so by decreasing the temperature, you'll be making the system less ideal. Not only because of this interaction issue, but also because by decreasing the temperature, you'll be increasing the volume, and hence you'll be having a lot of the same effects as you did in the last case. We've seen all this in the phase change diagrams. You see that if you increase the pressure of a gas, you make it behave less like a gas. In fact, at some point, you make it behave like a liquid. Similarly, if you decrease the temperature of a gas, you make it behave less like a gas, more like a liquid until it becomes a liquid. Now, what effect do you have if you increase the intermolecular attraction? So compare the idealness of helium versus water. Well, by increasing the intermolecular attractions, you're breaking some of those ideal gas assumptions. Hence, you will be decreasing idealness. So helium is more ideal than water. Water has a lot of hydrogen bonding between the particles, and hence a lot of attraction between those particles. And that is not part of our ideal gas assumptions, to have attraction between the particles. Similarly, increasing the volume of your particles, say going from helium to xenon, all noble gases. By doing this, your particles will have a greater relative volume within a container, and hence you'll be decreasing the idealness of your particles. Now, our ideal gas assumption allows us to use the ideal gas equation, PV is equal to nRT. But what if our particles do not behave ideally? Well, then we need to edit this equation to account for this non-ideal character. So first, let's say that you have a particle colliding with a wall. Now, consider that it has a strong attraction between it and other particles. Will it be colliding with the wall as hard as it was if there were no attraction between the particles? No, actually, because it's so attracted between the particles, it is going to have less force of collision against the wall and hence less pressure. By increasing the attraction between the particles, you'll actually be decreasing the measured pressure. And hence, to get back to ideal conditions, we need to correct for that. And so we want to add to the measured pressure to describe what the pressure would have been had there been no attractions between the particles. So this is a function of A. This is one of the van der Waals constants, which might sometimes be given to you. You multiply it by the number of moles within that container squared over the volume squared. Now, the volume of the container. This is assumed to be the volume of empty space within the container if your particles themselves have no relative volume. However, given that sometimes within the container the particles end up having relative volume, we need to subtract their volume to get back to the volume of empty space, which was initially our assumption. And so we subtract the number of moles of gas times the van der Waals constant for volume, B. And so this is just the equation which allows you to correct for PV is equal to nRT, although you most likely won't see it on the AP or other exams. And finally, gases generally behave ideally at very low pressures, for example, about 1 atmosphere. Now, this is PV over RT over here. Now, we know that PV is equal to nRT. So we know PV over RT should be equal to N. So assuming that we have 1 mole of gas within a container of volume 1 liter, we should have this ratio of 1. But as you increase the pressure, you will be leaving ideal gas conditions. And hence, your ratio here will change, hence that PV is equal to nRT equation breaks down. You can see that different particles kind of change this PV over RT ratio. Some increase, some decrease, and then increase. But importantly, you know that if you're at ideal conditions, then this ratio PV over RT is equal to 1. If you're not at ideal conditions, it's further from 1. Thanks for watching, guys.